Good morning. Any questions before we start having some fun? Any questions? None? By the way, I did send short notes which contains the stuff that we did last lecture. So as we go on, I will update those notes and send you new notes. Probably tomorrow, I'll send you your first homework. So watch, check your email now and then. Tomorrow, I think I'll be able to send it tomorrow. Okay? Any questions? None? So we were talking about strategic form games, modeling strategic form games so that we can make predictions and or prescriptions. We said a strategic form game consists of a four-tuple, quadruple, consisting of a non-empty and finite set N, which denoted the set of agents, denoted the set of players. And for each player, again, a non-empty set, it could be finite or infinite, which denoted the set of strategies of agent I. A function which mapped strategy profiles to outcomes, called the outcome function, which told us what the result of the game, the outcome of the game would be, given the actions, the strategies that the players played. And then, again, for each agent, a preference relation over the set of all possible outcomes, which we assumed for now is a complete and transitive binary relation over the set of all possible outcomes. So for now, what we understand from a strategic form game, that is a game in which agents have no information about the actions of the other agents. That is, in a game in which agents play as if they take an action simultaneously. So these games are also called, for that reason, simultaneous move games. Okay? So when we said model a game in a strategic form game, that's what we mean. For now, actually, we're going to make some changes today. We're going to drop the outcome function, but we'll come to that. So we started doing an example. We had the prisoner's dilemma game, which from now on, I'm just going to denote with PD, the prisoner's dilemma game. In the prisoner's dilemma game, there was two agents, so N was equal to 1, 2. Rather than using their names, we just labeled them with natural numbers. The strategy set of player 1 was C, D, confess, C standard for confess, D standard for don't confess. And the strategy set of player 2 was the same. So we're going to abuse notation and we'll just say S2 is equal to CD. But again, you should understand that the C which belongs to S2 is different than the C which belongs to S1. The C which is an element of S2 is an action of player 2. The C which belongs to S1 is an action of player 1. So they're two different animals. Okay, so the outcome, in order to specify the outcome function, we had to know what the outcomes were. These were things that we did last lecture. I'm just going to go fast over it. Actually, it's in the notes that I also sent to you. So the outcome is prisoner 1 goes to jail for 1 year, 2 for 10 years, 1 for 10 years, 2 for 1 year, both for 2 years, both for 5 years. And then we had the outcome function, which mapped CC, that is the outcome of this, well, we're going to call it game situation was if both confessed, then both would be jailed for 5 years. That was the story. If player 1 confessed, player 2 did not, because he's telling the truth, he gets a lighter sentence. Player 2, we know that he has committed the crime. He's also lying. He gets a heavier sentence. the symmetric case when player 1 confesses, player 2 does not. And if both don't confess, they'll go to jail from a lighter sentence. That's what we had. And the last thing, so we've specified what N is. We specified the strategy set. We specified the outcome function. So preferences. So the story told us that each suspect cares only about how much he is jailed for and prefers a lesser jail time to a longer one. So that implied that player 1 prefers the outcome 110 to the outcome 22. He prefers the outcome 22 to the outcome 55. And he prefers the outcome 55 to the outcome 10-1. Because we know that preferences are transitive and complete just by looking at this, we know that player 1 prefers the outcome 110 to the outcome 55 because of transitivity. So I don't have to write everything, okay? Similar for player 2. He prefers the outcome 10-1 to the outcome 2-2. Again, I'm going to abuse notation, and rather than writing it one by one like this, I'm just going to say he prefers the outcome 2-2 to the outcome 5-5, which is preferred by player 2 to the outcome 10-1. So whenever I give something like this, strictly speaking, this is not a meaningful sentence. Mathematically speaking, it's not meaningful. But when you're given this, you should read it in pairs. So this is one statement. This is another statement. And this is another statement. Okay? So far, so good. So that's what we did last lecture. And we were talking about numerical representations, but we'll get back to that. Okay? Now, if I look at this, 110, that's the outcome induced when player 1 confesses and player 2, suspect 2, does not. So this I can write as H of CD, the outcome induced by the strategy profile CD is preferred by player 1. 2-2, that's induced by DD, the outcome induced by DD. Okay? And similarly, for example, this statement I can write as outcome induced by DD is preferred by player 1 to the outcome induced by CC. Okay? And so on. Now, as a game theorist, why were we modeling this? We were trying to predict what the players would play, that is, predict which strategy they would choose, which action they would take, or prescribe what they should do, which strategy or which action they should take. We don't really care about outcomes. What we care is what they would or should do. Okay? So, you see, looking at this, there's an H on both sides. Again, this is not a mathematically meaningful information thing, but I can just erase these H's that's always there. You know, if something is always there, you can stop writing it, but keep in mind that it's always there. So I could just say CD is preferred by agent 1 to DD. What actually I mean is the outcome induced by CD is preferred by agent 1 to the outcome induced by DD. But I will just drop the outcome functions. Okay? Okay. So this way what happens is, given a preference relation over outcomes, I can obtain a preference relation over strategy profiles. Okay? Which is kind of nice because then I don't have to worry about the outcome function. I will have a simpler, a leaner model. Okay? So I can just specify who's involved, what can they do, what is their preferences over strategy profiles. Okay? So from this point on, whenever I say model the situation as a strategic form game, you have two choices. You can model it like this with the H, with the outcome function, in which case your preference relations should be over the set of possible outcomes, or, well, let me use this side, or model it, rather than a four-tuple, model it as a three-tuple. Where for each agent, Ri is a preference relation over set of strategy profiles over S, which was the Cartesian product of the strategy sets of agents. Okay. Again, we will abuse notation. We've become very abusive in this class. We will abuse notation and use the same symbol. Okay, Ri, I will use Ri to denote preferences over strategy profiles. I will use Ri to denote preference relations over outcomes. Okay, so, okay, the advantage of this is it's a linear model. It contains only 3 items. This is not. This contains 4 items. Okay. So the nice thing about this is linear, simpler. The bad thing about this is, in almost every situation that you face, in almost every story that you hear, preferences will be specified over outcomes. Okay? When you go ask somebody, you know, which party do you prefer? They would say, I prefer party X over party Y. They would not say, I prefer you and you and you voting to X and he and the other person voting to Y. They will not give their preferences over the actions of the voters. They will just say, I prefer party X to party Y. Okay? Preferences are almost all outcomes. Okay? So, which means that here specifying preferences will be easy because preferences are over outcomes. Here you'll have to do some work. Okay? So far so good? But usually we will use this. Okay, whenever we say model, you can use this too, but usually this is more preferred because it's a linear, simpler model. So far so good? So far so good? So here, if I was specifying, I was modeling the prisoner's dilemma game with this triple, there's no change in n, there's no change in SIs. Well, then Ri would be, I would say, CD, the strategy profile CD is preferred by agent 1 to the strategy profile DD, which what actually I mean is the outcome induced by CD is preferred by agent 1 but to the outcome induced by DD. Okay? So far so good? Any questions? Okay. So, now, last lecture we talked about numeric representation of preferences. Here, representing the preferences was not a big deal. Okay, using transitivity, only 3 statements took care of the whole thing. But in general, when the set of outcomes becomes larger, or when the set of strategy profiles becomes larger, specifying preference profiles while writing pairs is not always much fun. And also, sometimes, technically, it's not that easy to use with. So as economists, what we usually prefer is to use numerical representations of preferences rather than preferences themselves. Okay? What I call numeric representation is mostly what is called utility functions or payoff functions. So let me repeat the definition that I gave last lecture. This time, rather than using outcomes, I'm going to use strategy profiles. So let Ri be a preference relation over, well, any set, but the set that we're interested with here is the set of strategy profiles over S. A function okay, be careful, it's a function, not the function, a function UI, whose domain is S and range is the set of real numbers, is a numeric representation of Ri if and only if take any two strategy profiles, okay, S is at least as good as S prime for agent I, if and only if the number assigned to S by the function Ui is greater or equal to the number assigned to S prime by Ui. That's what, so it's, you just assign numbers to outcomes such that more preferred strategy profiles is assigned a larger number to less preferred strategy profiles. Okay, so far so good? Any questions? Okay, so if, actually, let me change this. Let me write the preference relation over strategy profiles rather than over outcomes. So 110 was induced by CD, 22 by DD, CC. That was 10-1, DC. Again, the way I read is, the outcome induced by CD is preferred by agent 1 to the outcome preferred by DD, and so on. Okay? So now let's, rather than writing the specifying preference like this, let's specify a numeric representation for numeric representation of the preference relation of agent 1. So there are 4 strategy profiles, so we should assign the number to each of them. What do you assign to CC? Yes? What would you assign to CC? Minus? Minus 5. Okay. What would you assign to CD? Minus. So there's 2 options, minus 1 and minus 10? Plus 10? So what are the minus 1, minus 10, 10, what else? Minus 9? So, sorry? Well, what is the key? So it's going to be a numeric representation of this preference relation. So the key is, by the way, this definition implies that, let me write that too here, S is preferred by agent I to S prime if and only if the number assigned to S under UI is greater than, okay, the number assigned to S prime by UI. So the only thing is, so we've assigned, so we started with this CC, we assigned minus 5. What is the relation between CD and CC? Well, so looking at transitivity, this is preferred to that, that's preferred to which. So by transitivity, we know that CD is preferred to CC. So the only thing we know is the number that I put in here should be bigger than this number. So it can't be minus 10, it can't be minus 9. But, yeah, minus 1 and 10 are both good. Which one? Minus 1. Okay. And then U1 of DC. So what do we know about DC? Okay. So where's DC? That's the worst. That induces the worst outcome. So I should assign a number which is smaller than minus 1, smaller than minus 5, minus 10. U1 of DD minus 2, right? So DD is worse than CD, so it should be assigned a number smaller than minus 1. But it's better than CC, so it should be assigned a number bigger than minus 5. Minus 2 will do the job. So does minus 3. Minus 4.6 will also do the job. Okay? So this is a numeric representation of the preference of player of suspect 1. It's not the only one. There's many. Okay? The nice thing about this is natural. What's it? You see, what is 5 here? It's the number of years that player 1, suspect 1, will be jailed if they both confess. And what did the story say? The story said they prefer being jailed. A lesser time is preferred to a longer time. So take the number of years that they're jailed, put a minus. That's it. Okay? So this is kind of a natural numeric representation, but it's not the only one. Okay? So far, so good? Any questions? Any questions? Yes, sir. So we could have, for example, rather than minus 2 here, we could have written minus 3.416. Okay? The key here is DD is worse than CD, is better than CC for player 1. So what I put in here should be less than CD because it's worse than CD. It should be bigger than minus 5 because it's preferred to CC. So any number between minus 1 and minus 5 would do the job. Okay? So far, so good? Any questions? Any questions? Okay. By the way, this is good, but we can summarize this all in a simpler way. If I look at this row, the first element of U is all C. The first element of U is all D. The second element in this column is all C. The second element in this column is all D. So rather than writing like this, I can be a little lazy and actually do this. First column, all C. First row, First row, all C. Second row, all D. First column, all C. First column, all D. So what I could do is put minus 5, minus 1, minus 10, minus 2 in here. Rather than writing it long like this, I could summarize the whole information in a table. Okay? So far, so good? So this will be the table of U1. Well, now I need a numeric representation of the preference relation of player 2. Actually, why not use the same table? Write down in this table a numeric representation of the preference relation of player 2. Okay? So which cell do you want to start with? Actually, let's do, you see, again, let me write the profiles. So 10-1 was induced by DC. 5-5 was induced by CC. Yep. Did I? Oh, yes, I'm sorry. Sorry, thank you. 110. Yeah. 110. Thank you. So that's CD, CC, DD, and then 10-1, DC. I got it right this time, right? Okay. So one easy way to give numeric representation is, this is the worst one. So I'll start with this. I'll give a small number to that. For example, so the rows marks the strategies of player 1. C, and then D, the columns marks the strategies of player 2. CD correspond to this. So for example, I could put a 0 here. That's the worst one. And then the second best one is CC. So I'll put a 1 here. And then the third best one is DD. I'll put a 3 here. And then the best one is DC for player 2. I'll put a 4 here. This is also a numeric representation of the preference relation of player 2. Okay? So far, so good? Okay. Now, the nice thing about this, so we also wrote U2 here. Well, I'll erase them, and we'll keep in mind that these numbers are numeric representations of the preference of players. The nice thing about this representation is, just by looking at this picture, I can tell everything that I need about the game. Okay? It's a 2-by-2 table, which would say that there's 2 players. So looking at this, I know that N consists of 2 players. By looking at, there's 2 rows. So I know that player 1 has 2 strategies, which are C, which are denoted with C and D. Looking at this, I can tell that player 2 has 2 strategies, which are labeled CD. And looking at these numbers, for example, -2 is bigger than -5. So I can conclude that for player 1, the outcome induced by DD is preferred to the outcome induced by CC. Why? Because -2 is bigger than -5. Okay. Again, looking at these numbers, I can deduce that the outcome induced by CC is preferred by player 2 to the outcome induced by CD. Because the second number here, which is 1, is bigger than the second number here. The second numbers are numeric representations of the preference of player 2. Okay? So this is a very efficient representation of a game. Just by looking at it, you see everything you need to know about the game. How many agents are involved? What can they do? What is their preferences? Okay? So far, so good? That's called a matrix representation of a strategic form game. I would like to call it a tabular representation of a strategic form game. Okay? So this is a tabular representation of the prisoner's dilemma game. Okay? By the way, as we said, there are many numeric representations. Rather than using this numeric representation for player 2, actually, this would have been this is also a numeric representation of the preference relation of player 2. This is kind of better than the first one. Why? Sorry? Natural. It's natural. And more than that, it's similar. You see the symmetry. Looking at this, you see the symmetry between the players, which might help you check your results. You know, if the game, for example, is symmetric, when we make predictions, I would expect those predictions to be somehow, whatever that means, symmetric. Okay? The symmetry was not that obvious in the first representation. Okay? So there are many numeric representations. Choose the one that is most useful, that will help you in analyzing the game. Okay? So far, so good? Any questions? Any questions? So this tabular representation. So if I say that this is a tabular representation of a strategic form game, what would you understand from this? First of all, how many players are there? There's only 2. What is the strategy set of player 1? It's T, M, B. The rows denotes the strategies of player 1. There are 3 rows, which means that player 1 has 3 strategies, and they're labeled with T, M, and B. What about the strategy set of player 2? L and R. What about the preference relation of player 1 between TL and ML? So what is the number assigned to TL? That's 2. What is the number assigned to ML? That's -1. Again, we're talking about player 1, so we look at the first numbers. 2 is bigger than -1, which means that player 1 prefers the outcome TL, the outcome induced by the strategy profile TL, to the outcome induced by the strategy profile ML. And then if I wanted to, again, let's choose MR TL. The order might be wrong. So what does player 2 think about these two strategy profiles? So MR, we're talking about player 2, so we check the second numbers. Believe it or not, this is a 2. So we check this number against MR, I'm sorry. MR, I should get a cup of coffee. MR, the number assigned to this is 1. TL, the number assigned to that is 1. So player 2 is indifferent between those two strategy profiles. That is, the outcomes induced by those two strategy profiles. Yeah, I should get some coffee. Okay? So far, so good? So far, so good? Any questions? Okay. So that's a very efficient representation. What if I had 3 players? What if I had 3 players? Well, then we would need a third dimension, something coming out of the blackboard. Actually, I was going to bring a third dimension with me, but in the hurry, I forgot. But roughly, it would look like something coming out of here. And then there would be this. Okay. So this would be, for example, the strategy X for the third player. This would be the strategy. So the vertical dimension would be played by player 1. The horizontal dimension would be played by player 2. And the one that is coming out of the blackboard would be played by player 3. And rather than having 2 numbers, we would have 3 numbers, where the first number stands for is the numbers assigned by the numeric representation of the preference relation of player 1. The second one, numbers assigned by the numeric representations of player 2. And then the third one, numeric representations of the numbers assigned by the numeric representations of player 3. Okay? But of course, you can't draw it like this. So what we will do is, rather than taking it out of the board, we will so that's the T dimension, M. So let me put the labels in any case. So that was L, R, and then I will not assign all of them, but let me just okay. So X, Y. So looking at this, there's 2 matrices, which, there's 2 tables, which means that there's 3 players. Okay. Player 1 has 3 strategies. Player 2 has 3 strategies. Player 3 has 2 strategies. Player 2 has 2 strategies. So the strategy set of player 3 is X, Y. And if I want to compare, I don't know, let's say M, T, X to B, L, Y. What am I looking? M, L, X, M, L, X. That's this cell. B, L, Y, B, L, Y. So I should put numbers in here. Okay. So if I'm looking at the preference relation of player 3, I compare this number with this number. 2 is bigger than 1. So player 3 prefers the outcome induced by this strategy profile to the outcome induced by this strategy profile. So far, so good? So far, so good? So the nice thing about this tabular representation is, with one look, you can see everything you need to know about the game. How many players are involved? What are their strategy profiles? What are their preferences? The bad thing about this is, well, if any one of the players has infinitely many strategies, you use a tabular representation. Even when they have, more than 5, 6 strategies, it becomes very cumbersome, okay? But when there is a few players, 2 or 3, okay, and each player has few strategies, this tabular representation of a strategic form game is very efficient, is very useful, okay? Unfortunately, not all games that we will be dealing with will fit into this framework, okay? Any questions? But whenever I give you a tabular representation, or whenever you see a tabular representation of a strategic form game, you should be able to read it like that. Deduce how many players there are, what the strategies of the players are, and what the preferences of the players are, just by looking at the table. Okay? Any questions? None? Okay. So, let's model another game. So we should feel comfortable with modeling because, if you can't model, you can't analyze the situation, okay? So let's do a few more examples with modeling. Let's do the second prize sale bid auction. So let me remind you the game. It was in the sheets that I distributed last lecture. So we had a single indivisible object that we would like to sell. We're going to use an auction to sell it. So what do? We ask each individual involved to write a number on a piece of paper without showing it to anybody else, seal it, submit it. We're going to give the object to the highest bidder. If there is more than one high bidder, rather than choosing one at random, to make our life easy for now, we'll sort them according to their numbers assigned to them, according to their index, and give the object to the high bidder with the smallest index, okay? And we'll ask him to pay the highest bid made by the rest of the agents. That's the description of the game, second prize sale bid auction, called also a Vickrey auction, which was studied by William Vickrey, a Nobel laureate. Okay. So it's obviously a game situation. There's more than one individual involved. They interact by means of actions. Their actions is making a bid. And then the welfare of each individual not only depends on what he or she does, it depends on how the whole group bid. Okay? So let's model the situation. First, you have to make a decision. Do you want the model using the outcome function or without the outcome function? Choose one. Without outcome function. So we're taking the recommendation of friends. So when we say model the situation as a strategic form game, we have to specify who's involved, what their strategies are, and what their preferences are. Or rather than using preferences from now on, if the preference relation admits, use the numeric representation, of the preference relation. Okay? So we have to specify this triple. Okay. So what is n? Well, there's n bidders, n individuals who would like to get the object. So we'll just denote it with integers from 1 to n. So 1 down, 2 to go. So take any player, any bidder, let's call bidder I. What is his strategy set? So when I say strategy set, we're asking what is the set of possible actions of this player. By the way, I forgot something. We have n bidders. Each bidder values this object at a maybe different value. Okay, so we will denote VI to be the value of the object to player, bidder, agent, I. Okay, so what is the strategy of player I? But it's time for a break. Let's take a break. After the break, we'll answer this question.